The particles that we encounter in nature, whether they are massive or massless, experience the gravitational interaction due to their energy content. Although the gravitational coupling is way smaller than other couplings in nature, the incorporation of gravity in quantum field theory interactions seems important. For example, in the description of our early universe or black hole physics. You might hear people addressing the incompatibility between quantum physics and general relativity, with the necessity to make efforts in order to find a desired theory of quantum gravity. So far, we can't say that we have this quantum gravity theory yet, despite there are some theories out there. Well, we don't have experimental evidence or any kind of hints as to which theory might be correct. Sometimes you might also hear people refer to string theory, or other times to loop quantum gravity. These theories have opened up new ways of looking at reality, for sure, but we might still be a long way from being able to test them. On the other hand, under certain circumstances, it is already possible to quantize gravity by using the well-known quantum field theory. This is possible only when we are dealing with weak gravitational fields. In this series of lectures, we will see how the concept of graviton emerges quite naturally by considering small deviations of the metric tensor from flat space-time. In particular, we will start from Einstein field equations of general relativity, and we will assume that the metric tensor is a small perturbation of the Minkowski metric. From there, we will derive Einstein field equations up to second order of the perturbation. We will see that the equations derived in this way are those of a massless spin-2 field. After that, we proceed to solve the equations and find a way to express the metric tensor in terms of the source. After dealing with the classical equations, we switch to the quantum realm by quantizing the field, recalling the concept of path integral and partition function. The quantum theory will allow us to derive the average number of gravitons and understand the concept of polarization of gravitational waves. In all the derivations, it is assumed that the student is familiar with tensor calculus, Einstein field equations, quantum field theory in the language of path integrals, complex calculus. Therefore, it goes without saying that the course is aimed at students who master these concepts. On the other hand, the equations will be derived step by step, leaving the time to digest the concepts. As a reference, the videos are inspired by two books on quantum field theory written by Manukyan. Let me stress that it is not necessary at all to possess these two books here that are listed, Quantum Field Theory 1 and Quantum Field Theory 2. You don't have to possess these two books in order to be able to follow the lectures. More insights will be added with respect to the books.